Okay, so these are the notes for 7.4. First thing you need to know is we're going to have to talk about this chi-squared distribution table. Chi-squared distribution is a distribution that is obviously not symmetrical, but we're gonna use this to be able to do standard deviation and variance confidence intervals. So I want to help you understand a few things about this table, and then we'll go into the notes and reference this table throughout. First thing you need to understand is that chi-squared gives us the area to the right of our cut value, okay? And so one thing that you'll want to know is that when we do the chi-squared table, you'll have to have, you know, if you, let's just grab up a pen here. If you wanted, say, 90% confident interval around your standard deviation or variance, that would mean you'd be leaving 5% on each tail. Okay, so 5% to the right would be corresponding to 0.05 to the right, which is right here. Okay, 0.05 to the right. Well, for the other value, you know, again, the chi-squared chart only gives us to the right. Well, to the right of that left cut would be 95%, because we're leaving the 5% behind. As you can see here, the chi-squared of 0.95 is here. So you can see I've color-coded this. Not everybody has a set of coloring or highlighters to be able to highlight all of the lists. So a simple way to build the same coordination is to just label them A, B, C, D, E, and then relabel backwards E, D, C, B, A. Okay, so if we have these labeled A, B, C, D, E, and then E, D, C, B, A, so we know that they go together. The next thing we kind of want to identify on this chart is which columns represent which confidence intervals. So for instance, this 90% confidence interval we said represented this 0.05 and the 0.95. If you look at the right side, it's a little bit easier to tell. If I want 90% confident, that means I'm leaving 10% out, and half of that would be 5%. So you can see the 5% right here. So column D is 90% confidence interval. E would be 0.1 on the right tail. If I take 0.1 on the left tail, that makes 0.2, so I'd have an 80% confidence interval. If you use the same logic for all of these, C should be 95% confidence interval, B would be 98% confidence interval, and A would be 99% confidence interval. So that's how we use this chart. The left side of the chart is our chi-squared on the left, and chi-squared on the right will be the right side of the chart. Degrees of freedom right here, that column tells us which line to use, which row to use, and the degrees of freedom is 1 less than your sample size. Okay, so let's go back and talk about how we're going to use this information. When we're doing the confidence interval for variances or standard deviations, we're going to use the chi-squared distribution. It's similar to the t-distribution in that it's a family of curves based on the number of degrees of freedom. It is skewed to the right, but if we get the degrees of freedom high enough, we can actually bring it a little bit close to the normal distribution. You can see that as the n goes up, this graph pulls to the right and becomes more uniform or more symmetric. Because the chi-squared is skewed, two values have to be found for each side of the curve. We have what's called the chi-squared right and chi-squared left. And so we're going to find that on our chart. If we look for the chi-squared on the right, when n is 25, first thing we kind of want to identify here is that if n is 25, then the degrees of freedom is going to be 24, and we're looking for 90% confidence. So when I come to my chi-squared table, 90% confidence is column D, and I want to go for a, what do we say, 24 for my degrees of freedom. So I'm going to come on my degrees of freedom 24 over to 13.848 and 36.415. The one on the left is the chi-squared left. The one on the right is the chi-squared right. So you should be able to find these values on the chart. This is not one we're going to be able to use the calculator to produce. So we're going to have to do this by hand. So this chart is important that we know how to read. When we actually calculate the boundaries around the variance, right, the actual population variance or the population standard deviation, these are the formulas that we will use. N minus 1 times the standard deviation squared, or S squared is the variance, so if you know the variance, you can just plug it in without squaring it. But that is the sample standard deviation, or sample variance. And then we put the chi-squared right value on the left and the chi-squared left value on the right. That's because the chi-squared right value is bigger. So when I divide by that big number, I will end up with a smaller boundary on the left and a bigger boundary on the right. We don't square this. This is literally just called the chi-squared right value, chi-squared left value from the chart. So let's look at a really simple example. We got the 95% confidence interval for the variance and for the standard deviation. And so we want to go ahead and create these bubbles around the population values. The formula for the variance confidence interval is n minus 1 times s squared over the chi-squared on the right. And over here it'd be the same thing, n minus 1 standard deviation squared over chi-squared left. Okay, so we're going to start by saying what our n is. It says here we've got a 95% confidence interval for the variance and standard deviation of the nicotine content in cigarettes manufactured if a sample of 20 cigarettes has a standard deviation of 1.5. So we're going to start with 20 minus 1 times the standard deviation of 1.6. That needs to be squared. And that's all going to be divided by some set value that we're going to have to pull from the chart. Okay, and it's the same number, but it's over a different chi-squared value. So I go to the chi-squared table. We're looking at 19 being our degrees of freedom. Okay, and we wanted 95% confidence interval, which is column C. So that would give me the 8.907 and the 32.852. These are going to be my two values that I will use to produce my, again, 95% confidence. So I would put those two numbers in the bottom here. I'm going to get one of those numbers written down, 8907. 8.907, and it was 32.852. 852. Okay, so then if I take those numbers and evaluate that in my calculator, I'm going to produce the cut values, or the bubble values, if you will, for our confidence interval around the cigarette question. Let me get to the right. I need the answer. Let me look it up here real quick. You just plug that into your calculator and you'll produce numbers. Oh, I did this backwards. These two numbers need to flip-flop. Someone probably already knew that. This is the smaller number. It's the left number, but it goes on the right, and the right number goes on the left when we do the calculation. So if we do that, we'll end up with something around 1.5 and 5.5. And then if we square root those two numbers, we'll get the standard deviation confidence interval from 1.2 to 2.3. So those are how we build our confidence intervals. In the next example that we get, it's a 90% confidence interval, but they don't give us the standard deviation, which is the one piece of information we have to have. So to find the standard deviation, we're going to have to use the table in our calculator. And so I'm going to grab my calculator real quick. I'm going to go to Stat and Edit. Over in L1, I'm going to want to put in this set of data, which is 59, 54, 53, 52, 51, 39, 49, 46, 49, and 48. If I do that, go to Stat, slide over to Calc, and I'm going to run one variable calculation. variable stats, I'll do it on L1 and calculate. Right here, Sx is my standard deviation for the sample, which would be 5.312. 5.312. And now that I have that information, it's the same n minus 1. I've got 10 data values, so 10 minus 1 is 9 times my standard deviation, 5.312 squared, over my chi-squared value, and then I do the same thing over my other chi-squared values. So again, we're looking at 90% confidence. My degrees of freedom should be 9, one less than what I have in my sample. So I'm looking 9 degrees of freedom, 90% confidence. 90% confidence would be column D, this blue one. I'm looking for a sample size of 9. That's 3.325 and 16.919. Plug it in, do the same exact calculation, and you should come out with, again, if you do it wrong, if you mix them up, and you put the left one on the right, and if you mix those up, the good news is just put them in order. If you make a poor calculation, as long as the smaller number goes on the left when you're done, when you have your actual results, you'll be okay. So 15 to 76.3. And then if we square root that to get the standard deviation confidence interval, we'll have 3.87 up to 8.73. Okay. So this is kind of to close out the chapter. We did several different confidence interval bubbles that we've been building. Let's talk about which ones we build and when. So you kind of look at this, we've got sample mean, sample mean. Okay, if we use the sample mean, we're going to produce a bubble around the population mean. But there's a couple of variations. If I have the population standard deviation, it's different than if I have the sample standard deviation. These two are different because of the information I have. If I have x bar and I have sigma, then I can use the z interval test on my calculator to produce the data, or the boundaries. However, if I have the x bar and the sample standard deviation, then I had to use the t interval. Okay? I didn't use the z interval, I used the t interval for that. Understanding when to use which test, or which interval test is important. The third option was what happens when you're using the sample proportion. Instead of a sample mean, we use a sample proportion, which gives us a proportion value. And if we know p hat, the sample proportion, then we can run a 1 proportion z interval test in our calculator. With 7.4, what we did today, there is no calculator program, so we use S or S squared, the standard deviation or variance, and the chi-squared chart to be able to produce those boundaries. All right, good luck, guys. We'll see you in class. Hopefully this helps out.